Welcome to the next lecture on statistical methods in AI and machine learning. In this lecture, what we are going to do is we are going to look at structure learning algorithms for Bayesian networks. Okay, we are going to look at specifically four types of algorithms which use fully observed data, algorithms which use partially observed data, and algorithms which use either the Bayesian approach or the maximum likelihood estimation approach. Okay. So in last class, what we did is we looked at the Bayesian approach for learning the parameters of a Bayesian network under the assumption that the data was either fully observable or partially observable. And one of the complaints I guess I got on Piazza was that there were too many mentions of the word Bayesian. And this is unfortunate because uh, of some of the names that exist in the field, I should say. Uh, I like one mention of the word Bayesian, and I don't like the second mention of the word Bayesian, which is included on the slide. So the word Bayesian inference, right, which is the uh, main approach behind Bayesian learning, comes from statistics. Okay, and the reason it's called Bayesian inference is that we use the Bayes rule to estimate the posterior by taking a product of the prior and the likelihood. Okay, so I like the word Bayesian inference being used because we are actually using the Bayes rule to compute the posterior. However, in my opinion, Bayesian networks is kind of a misnomer because we actually never use the Bayes rule uh, in the context of Bayesian networks. What we actually do in Bayesian networks is that we use the chain rule, right, and apply conditional independence properties on top of the chain rule. Okay, so if I were to go back in history and rename Bayesian networks, I would call them as sparse chain networks because they're using the chain rule of inference. Okay, if you want to suggest a better name and change the field, uh, you're welcome to do so. After all, right? What's in a name, right? Give something a cool name, market it, and you're famous. Okay, so help me, right? Changing the word Bayesian networks to something better, right? Which actually identifies it and differentiates it from Bayesian inference. Okay, so enough of ranting about the name Bayesian networks and Bayesian inference. Okay, let's come back to the class where what we are going to do is we are going to look at structure learning algorithms for Bayesian networks. Okay, so let's look at the first approach where we are learning the structure of the Bayesian network under the assumption that the data is fully observable and we are using the maximum likelihood estimation approach. Okay, if you remember, the goal in maximum likelihood estimation is to find a model such that the likelihood of the data is maximized. Okay, we are interested in the structure learning problem here, and as I mentioned before, structure learning includes parameter learning as a sub-problem. Therefore, whenever I say that I want to learn a maximum likelihood structure in the context of Bayesian networks, I want to learn the maximum likelihood directed acyclic graph, the maximum likelihood DAG, or I should say, and I also want to learn the parameters or the conditional probability tables associated with that DAG. Okay, so that's our goal. Unfortunately, this goal is problematic. Okay, this is because a so-called complete DAG is provably the best structure. Okay, so if I want to perform MLE learning in the case of fully observable data, all I have to do is just output the complete DAG and learn the parameters of that DAG using the closed form estimates that we derived for the FOD case. Okay, how do I know this? I know this because we can easily prove a theorem which says that if you're given a DAG G, then any DAG G star that is constructed from G by adding edges will be such that the likelihood of G star will be greater than or equal to the likelihood of G. Okay, so you take any DAG structure, let's say something like this. Okay, and let's call this G. Okay, and you add any edge to it. So let's say I add that edge. Okay, and this new graph, let's call it G star. It turns out that G star will always have higher likelihood than G on the training data. Okay, so by induction, we can easily prove that the complete DAG will be the best structure. Okay, so what have I just said? What I've just said is that MLE learning, okay, is problematic and MLE learning cannot be done. So how do I get around this problem? The way I get around this problem is by alluding to our favorite machine learning principles, those of overfitting and underfitting, as well as bias versus variance trade-offs. So we know that whenever our Bayesian network has small number of parents, which means that the DAG associated with the Bayesian network is a sparse graph, right? Then the Bayesian network will typically underfit. Another way of saying this is that the Bayesian network will be very biased. However, it will have low variance. Okay? If I have a Bayesian network in which each variable has large number of parents, or I should say maybe some variables have large number of parents, then that Bayesian network will yield a dense directed acyclic graph. And such Bayesian networks will overfit the data, right? They will overfit the training data and will have poor generalization performance. If you remember, the goal in machine learning is not to do well just on the training data, okay? But the goal in machine learning is to do well on this so-called unseen examples or test examples, okay? And sometimes this is called as generalization. And whenever you have graphs which are, or whenever you have DAGs, I should say, because we are learning Bayesian networks. Whenever you have DAGs that are dense, then those DAGs will have poor generalization performance. Why? Because they will have low bias, but their parameters will exhibit very high variance. Okay? So in general, and sometimes this principle is also called as the Occam's razor, what you should do is you should prefer sparser structures or these so-called simple models, even if the model is unlikely to capture the data generating distribution accurately. Okay, so it might be the case that the data generating distribution requires a DAG having 5 million edges, let's say for some domain that you're trying to work on. However, because you only have access to limited amount of data, for better generalization performance, and in order to estimate the parameters of such a model accurately, what you should do is actually learn a much sparser structure than 5 million edges. So if let's say your data has something like 10,000 points, maybe you'll only learn structures that have something like 1,000 edges. and no more than 1,000 edges. Although maybe the uh, full data generating distribution might have 5 million edges. Okay? And the reason actually boils down to this simple thing. The simple thing is that we have access to limited amount of data. Okay? And if we learn a dense structure, our variance will be so high that our learning will be useless. Okay? Our generalization performance will be very, very bad. So typically, what happens is that the bias versus variance trade-off can be represented by a graph which looks like this. Okay, so let's say this is the likelihood, okay, and this is the number of edges in the graph. Remember, what we want to do is we want our likelihood to be as high as possible. But not only the likelihood on the training data, but also the likelihood on the test data. So this is what typically happens with the training data likelihood. As we increase the number of edges, you start with small likelihood and you gradually increase and reach this so-called best possible likelihood, right? Where you actually have a uniform distribution over the data and nothing else. That's the best likelihood that you can hope for. But that model will generalize poorly. What I mean by that is that if I plot the likelihood on the test data, so this is the likelihood on the training data, which will keep on increasing as I increase the number of edges, the likelihood on the test data will follow a different pattern, right? So initially what will happen is it will increase similar to the training set likelihood, but after a point it will start decreasing. Because here what is happening is that you are overfitting on the test data, or I should say overfitting on the training data, and therefore your test data likelihood is much, much smaller. So what you want to reach is that point over there, where you have the perfect balance between this bias and variance. Because high bias and low variance models will be these guys, right? And low bias and high variance models will be those guys. And what you want to do is reach this perfect balance between bias and variance. Okay? So that's the plan here. The plan here is to prefer these so-called sparser structures. Okay. So how do we solve this underfitting and overfitting problem, or this achieve this perfect balance between the bias and the variance in the context of structure learning in Bayesian networks? Okay, the idea is actually fairly simple, right? The first thing that we can do is we just have to introduce more bias in the model rather than learning a very low bias model that is a complete graph. Okay, and the way we put bias in our model is we put constraints on the type of Bayesian networks that will be induced by our learning algorithm, right? So induced is nothing but learn, right? So this is a word that I'll often use, right? Because we are doing induction rather than deduction, right? So inference is you're given a model and you deduce something, okay? So you have a specific query. So what you try to do is from a general model, you try to answer a specific query. While learning is the opposite problem, right? You're given examples and you're trying to do induction, which is you're trying to learn a general model based on some specific examples. Okay, so that's why sometimes learning is also called as induction. Okay, enough said. So the idea here is to put constraints on the type of Bayesian network that is learned by the learning algorithm. Some example constraints that we will be able to put are things like learn a Bayesian network such that the tree width of the Bayesian network is bounded by a constant. Okay, so tree width is kind of a measure of sparseness, right? But it's also a measure of complexity of inference. And in general, we want our complexity of inference to be low. And why do we want our complexity of inference to be low? Because we want to do something useful after the model is learned. And if the tree width of the model is bounded by a constant, we can use exact inference algorithms such as the junction tree algorithm or the bucket elimination algorithm to solve a large variety of inference tasks. Okay? The second type of constraints that we can put on the Bayesian network are to use a scoring function which penalizes models having large number of edges or parents. Okay? Such constraints are called as soft sparsity constraints, and we'll see what they are. Okay? Sometimes what you'll do is that you might bias the model too much. Right? In the process of putting constraints on the type of Bayesian networks that are being learned, you might bias the model so much that you won't achieve this so-called perfect balance between bias and variance. Okay, so one way of circumventing this problem is to use latent variables. Okay, and we can use latent variables to not only reduce the bias, right, or underfitting issues, but we can also learn more diverse models, right, which capture different parts of the distribution very well, right? And in such cases, what happens is that even if your model is very sparse, okay, it can actually capture a large number of dependencies that exist in the original model from which the data is being generated. Why? Because if you remember, if I give you two tree Bayesian networks which are connected by, let's say, one single variable, right? And let's say that single variable is a parent of uh, all the other variables in the Bayesian network, right? Then eliminating the variable will create a clique between all the variables. Okay, so just to demonstrate this idea, so think about it this way, right? So let's say I have a latent variable L, right? And I give you two Bayesian networks over here, okay? And let's say it turns out that this latent variable is a parent of every other variable. So this is a tree Bayesian network, agree? Okay, so this is a tree Bayesian network over x1, x2, x3 if I remove the latent variable. However, when I eliminate the latent variable, what happens? When I eliminate the latent variable, I create a clique over x1, x2, x3. So in a way, I'm able to model many dependencies using the latent variable. Okay, so that's what we can do. We can actually reduce these, or in some cases, completely eliminate these underfitting issues by using latent variables. And we'll see like some models that use this aspect. Okay, so nowadays these latent variables have become very common. At a very high level, most of the deep architectures are nothing but complex latent variable architectures. And finally, we can be good machine learners, right? And use the Occam's razor to our advantage by performing something called model selection, where we start with a biased model and then reduce the model, the bias of the model gradually using either cross validation or a separate validation set to choose the correct model. Okay, so these are some of the things that we are going to do in this class. So the first thing that I'm going to cover, right? So I'll cover three things essentially: learning bounded tree width models, then using latent variables, and then using scoring functions. Okay, so let's start with learning bounded tree width models. So let's start with some good news, right? The good news is that if your Bayesian network, right, or if your, let's say, data generating distribution or the distribution that you want to learn has tree width 1, okay, then such models can be learned optimally in polynomial time. Okay, so recall that Bayesian networks having tree width 1 are called singly connected Bayesian networks. What I mean by singly connected Bayesian network is that each variable or I should say all variables, have at most one parent. Okay? So such Bayesian networks are called singly connected Bayesian networks, and their primal graph is nothing but a tree. So primal graph is the same as the model graph. So remember, in the model graph, what you do is you marry the parents, but since each variable has one or fewer than one parents, there is no marriage to be done, right? So the primal graph will be the same, will have the same undirected structure as the original DAG, okay? And so the primal graph is also a tree. So that's the good news, right? So if you want to learn trees, life is beautiful because you can do that in polynomial time. Now comes the bad news. The bad news is that if you want to learn Bayesian networks, having tree width greater than 1, then it turns out to be an NP-hard problem. Okay? So even learning things like polytrees is NP-hard. So if you remember, polytrees are nothing but directed acyclic graph, which are trees, right? But variables can have more than one parents. So here is an example of a polytree. Right? So as you can see, that the DAG is a tree, but it's not a singly connected network because x2 has two parents. This variable has two parents. Okay. So before I present the I should say the more efficient algorithm or the polynomial time algorithm for learning tree Bayesian networks, let us consider the naive approach, right, for learning tree Bayesian networks from data under the assumption that we are using the fully observable, or under the assumption that our data is fully observed, right, or the FOD case. Okay, so here is a naive algorithm. The idea is we generate all possible singly connected tree structures, store those tree structures in a set, let's call this funny letter T, okay, and then run the following iteration over elements of the set represented by this funny letter T. Okay. For each tree in T, we do the following. We learn the parameters of the tree by using the closed form solution for the FOD case. If it turns out that the likelihood of the tree with its parameters is better than the current best solution, which is stored in best LL, okay, then what do? What you do is you designate that particular tree as the best tree. And at the end of the algorithm, you just return this so-called best tree. Okay, so the idea is generate all possible trees, right, and then select the best among them based on the log likelihood score. That's the idea in the algorithm. Now my favorite question, right? What is the complexity of this algorithm, time and space wise? Okay, so time wise, the complexity is super exponential. Why? Because think about the number of trees that you can generate. It's a very large number. In fact, even if I restrict myself to these so-called binary trees, right, the number of binary trees is a huge number, right? So the number of all possible binary trees is a huge number. So that's why the time complexity is super exponential, and this algorithm is useless in practice, right? The space complexity is also super exponential in this case because the way I've presented the algorithm, I'm storing all these tree structures in a set called T. However, you can make this algorithm space efficient by having a process that generates a new tree every time you need a tree, right? And that process is exhaustive in the sense that it is able to generate all possible trees that are out there. Okay, so if you use that algorithm, the space complexity will be linear, the time complexity will be still super exponential, and this problem and this algorithm, I should say, is impractical. So why did I present this algorithm? I presented this algorithm because you can see that in the absence of more efficient algorithm or more efficient theorems that enable, or I should say, formal work or theorems that enable efficient algorithms, this is the best you can do. Okay, so instead of trees, let's say we were thinking about the best possible DAG or the sparsest possible DAG, this naive algorithm could be used, right? How can it be used? So let's say you have some constraints on the number of parents that each variable can have. What you have to do is generate all possible Bayesian networks such that the number of parents is bounded by 3. Okay, and then do a search over that space. But the good news, right? Since we are in the space of tree Bayesian networks, okay, we can actually prove, and Chow and Liu in 1968 proved that for trees, and I should state that this theorem does not apply to graphs, they proved that maximizing the log likelihood of data under the assumption that G is a tree is the same as maximizing the sum mutual information over X and U, where U is the parent of X. Okay? So to define mutual information, the mutual information between X and U is nothing but the expected value of PR of X comma U divided by, or I should say log of PR of X comma U divided by PR of X times PR of U. Okay? So what the mutual information does is, at a very high level, it measures the dependence between two variables. Higher the value of the mutual information, higher the dependence. Okay? And mutual information is 0 when X and U are independent. Okay? So why is mutual information 0 when X and U are independent? Because when X and U are independent, we know that P of X comma U will be equal to P of X times P of U, which means that this will be equal to 1, right? That ratio will be equal to 1, and log of 1 is nothing but 0. So in that case, the mutual information will be equal to 0. Okay? So it measures the dependence between two variables, and if the two variables are highly dependent, then their mutual information value will be high. Right? If the two variables are independent of each other, then the mutual information value will be 0. Okay, so what does this mean? So what it means is that instead of maximizing the log likelihood of data, now all we have to do is we have to maximize or find a tree such that the mutual information of the tree is the maximum. Okay? So a consequence of this result is that we have to compute mutual information between all pairs of variables X and U, and then find a spanning tree, because remember, we want to find a tree such that the sum mutual information is maximized, right? So one way of looking at this is like find a tree, right, from a complete graph, which is such that the weights of the edges in the graph are the mutual information score. Then find a spanning tree of that graph such that the spanning tree has the maximum weight. Okay? So that's why this algorithm is very easy. Okay? So here is an example of the algorithm, this so-called Chow-Liu algorithm, which learns optimal trees given complete data. Okay, as I said, what you have to do in the first step is you construct a complete graph with edges that are weighed by the mutual information score between the two variables. Okay, so let's say you are given four variables a, b, c, d, right? Then you will draw a complete graph over a, b, c, d, and then weigh the edge between a and b by the mutual information between a and b that is computed from data. Okay, how do you compute the mutual information between a and b from data? All you have to do is, if you remember, right, the formula for mutual information is nothing but sum over xu p of xu log of p of x comma u divided by p of x times p of u. Okay, so when you're given data, how do I estimate p of x comma u? This is nothing but the number of times x comma u appears in the data divided by the total number of data points. Let's call it n. Similarly, p of x can be estimated as the number of times x appears divided by n. Same thing with u. Okay, so once you have these estimates, I can just substitute these estimates in the formula, and I can compute the mutual information score. Okay, so now you have a graph in which the edges are labeled by the mutual information score. The next step in the algorithm is to find a maximum spanning tree over that complete graph. Okay, so you can verify that the maximum spanning, and the maximum spanning tree, I should say, can be easily computed using the Kruskal's algorithm. So for this complete graph ABCD with the weights given on the slide, the maximum spanning tree turns out to be A, C, B, and D. So those are the edges. And you can go home, and since you're already home, since this is an online class, you can verify that actually ACBD is the maximum spanning tree here. So once you have found the maximum spanning tree, you can convert the maximum spanning tree to a rooted tree, right? So think of the rooted tree with the root at the top, and then orient the edges in the Bayesian network from top to bottom. Okay, so an example will be, let's say I think of B as my root. Okay, so I'm drawing after selecting B as the root, I'm drawing it as a rooted tree. Okay, so that will be the rooted tree if I select B as the edge. So all the orientation of the edges are from top to bottom. So that's my Bayesian network. Okay, similarly, which is the one given on the slide. Okay, similarly, if I choose A as the root, I can draw it as a rooted tree, right? A is the root, A goes to C, right? C goes to B, and B goes to D, right? So the arrows will be like that. Okay, and I'll get the Bayesian network which looks like that. Then you can select any one of these networks, it doesn't matter. The log likelihood score on both these networks will be the same. Okay, then what you do is you learn the parameters of the Bayesian network, any tree that you select, using the FOD closed form solution that we discussed in our previous class. Okay, and once you complete these steps, the output of the algorithm will be a Bayesian network as well as its parameters. And the Bayesian network in this case is going to be a singly connected Bayesian network or a tree Bayesian network. Okay, so one homework problem that I want you to consider and also prove is, why would the log likelihood score on these two networks be the same? Okay, another way of saying this is proving that the distribution, right, under the assumption that the parameters of the distribution are learned using the closed form solution for the FOD case, the distribution represented by this Bayesian network is the same as the distribution represented by that Bayesian network. Okay? And in general, if you take a maximum spanning tree, okay, or for that matter, any tree, and use the prescription that I just gave you for converting the tree to a singly connected Bayesian network, then the distributions represented by all the singly connected Bayesian networks that can be computed from this tree will be the same. Okay, so that's the point. Okay, so now comes the favorite question, right? Since it's a computer science class, what is the complexity of the Chow-Liu algorithm? So it turns out that the complexity of the Chow-Liu algorithm is n square m, where n is the number of variables and m is the number of data points. Okay, this is easy to say because we'll have to compute. So if n is the number of variables, then the complete graph will have O of n square edges. Okay, and in order to compute the statistics required for computing the weight on the edge, I'll have to go through the data. I'll have to go through each example at least once. Okay, so that's why the complexity will be O of n square m at least. Where does the n square log n come from? The n square log n comes from the fact that the Kruskal's algorithm has a complexity of n square log n. Okay, so the overall complexity is O of n square m, where m is the number of data points, plus n square log n. And typically what will happen is that m will be much larger than log n, okay, and more closer to actually n, the number of variables, and in actually many cases much larger than n, which is the number of variables. So the complexity of this algorithm will be typically, you can write it down as O of n cubed. Okay, so it will be at least O of n cubed, because typically the number of data points will be much larger than the number of variables in the model. Okay, so what's wrong with the singly connected Bayesian networks? I mentioned it in the first few slides, right? What's wrong with them is that they are very biased models. Although they have very low variance, their bias is so high that they'll be useless in practice, in the sense that they will have very poor generalization performance. Okay, so how do I improve the generalization performance of Chow-Liu trees? One easy way of improving the generalization performance, and by Chow-Liu trees I mean Bayesian networks which are singly connected. Okay, so these are sometimes also called as Chow-Liu trees, because they are learned using the Chow-Liu algorithm. So one easy way of improving the generalization performance of Chow-Liu trees is to use mixtures of tree Bayesian networks, where you add just one latent variable, I should say, and let's say the latent variable has k values. Okay, so since this is a mixture variable, one way of looking at it is that you have a collection of k Chow-Liu trees, okay, each with their parameter set, let's call it theta I. Okay, and in addition to that, you have parameters which are associated with the latent variables, which are these PIs. Okay, and these PIs are called as mixture weights. We will say that these PIs are nothing but the probability distribution, or the unconditional probability distribution over the latent variables. What I mean by that is that each one of these PIs will be greater than or equal to 0, and their sum will be equal to 1. Okay, so think of the distribution represented by uh, this mixtures of tree Bayesian networks as P of L, where L is the latent variables, times P of X given L. Okay, so P of L is given by Pi, and P of X given L is given by Qi of X theta. And if I want a distribution over P of X, what do I have to do? All I have to do is like sum out the latent variable, which is the same thing as saying that I want to sum out for the k values, right? And this is where this formula comes from. Okay, so that's our model, right? So we have one latent variable, which is this mixture variable, and we have k different Chow-Liu trees. How do I learn this model? Well, you already know how to learn this model, right? We can use something called the EM algorithm, right? Because now we are in the partially observed data case. Why are we in the partially observed data case? Because we have an extra variable which is hidden or latent. Okay, so how does this algorithm work? Straightforward, right? Now you guys are experts in the experts at the EM algorithm. Okay, so you start with a random model. What I mean by a random model in this case is you randomly choose the trees, the structure of the trees, as well as the parameters of the trees. Okay, and then you also randomly choose these PIs. So the parameters of these models are nothing but, let's say, P1 to Pk, and then theta 1 to theta k. So the thetas are the parameters of the Chow-Liu trees, and these P1 to Pk are nothing but the mixture weight. So you select P1 to Pk and also theta 1 to theta k randomly. Then you repeat the following two steps until convergence. The first step, which is the E step in the EM algorithm, you complete the data using your current model. So completing the data in this case is assigning probabilities to each one of the k values of the latent variable, right? So each data point will now be equal to k data points. And once you have completed the data, you estimate the parameters of the model again, right, using the completed data. So how do I estimate the parameters of the model using the completed data? Estimating P1 to Pk is easy, right? All you have to do is just count how many times or just add the weights for each of the components, right, and divide the weight by n. That is how you can update PIs. How do I update theta i's? To update theta i's, all I have to do is run the Chow-Liu algorithm for that component and weighted data, and I'm done. Okay. So the mixtures of tree Bayesian networks, although it's a very, very simple simple approach, right? You just add like one variable, and this algorithm is typically very fast because it uses the Chow-Liu algorithm. Although it's very, very simple, it often performs very well in practice. Okay. To improve the performance further, what you can do is you can use more sophisticated deep learning approaches where you induce a deep network of latent variables. And there are various approaches in literature. One which is developed in my lab called cut-set networks, as well as sum product networks, which was developed in Professor Pedro Domingo's labs, where I was a postdoc at University of Washington, as well as probabilistic sentential decision diagrams, which are researched by several researchers at UCLA, including Adnan Darwish and Guy van den Broek, right? So we are looking at the book by Adnan Darwish. The same Adnan Darwish is also involved in learning these so-called latent models and tractable models from data. Okay, so that's how we can improve the performance of chow liu, right? It's a very simple algorithm, right? And you improve its performance by adding latent variables. What about bounded tree with Bayesian networks? So it turns out that learning even tree with two networks is an NP hard task, and therefore there is no hope for any efficient algorithm to exist. The best known approach for learning Bayesian networks having tree width larger than 1 is by Elidan and Gould, which appears in Journal of Machine Learning Research, and it's a nice article from 2008. However, in practice, and we have extensively experimented with this, adding actually latent variables, right, and using these so-called chow liu trees works much better than learning bounded tree with Bayesian networks in many cases, right? So on many data sets, mixtures of trees will dominate the Elidana and Gould algorithm in terms of log likelihood score. Okay. So one homework question that I want you to think about is that even though the LL score of mixtures of trees will be typically greater than or equal to this algorithm by Elidan and Gould, who learn bounded tree with Bayesian networks, why would you prefer the Elidan and Gould method, right, to mixtures of trees? Okay, and this is a homework question that I want you to think about. Specifically, I want to give you a hint. Think about map inference, or the maximum a posteriori inference, right? Not the MPE inference, but the map inference. And how will Elidan and Gould's method, right, be better at map inference as compared to doing map inference on mixtures of trees? Okay, so think about it, and that is one question that I'll try to answer during our review session or QA session. Next, what we'll do is we will look at score-based methods for learning the parameters of a Bayesian network from data, or I should say learning the structure of the Bayesian network from data. As we saw, in the context of structure learning, using likelihood is problematic because the complete DAG will always give you the best log likelihood score on the training set. In order to circumvent this problem, what we will do is we will add a penalty term such that the penalty term will prefer a simpler model over a more complicated model. And what I mean by a simpler model is a sparser model over a denser model. In particular, we will express the scoring function as likelihood plus penalty, where penalty is given by negative of phi of m times the dimension of g, where phi of m is a function of the number of data points. Okay, so as we get more and more data, we will allow our models to be more and more complicated or more and more denser. But if we have fewer examples, what we will try to do is we will try to select models that have sparser structure. Okay, so that's why we have a function which is a function of the data points. The second term in the second subterm in the penalty is dimension of g, which is the number of parameters in the Bayesian network, such that the Bayesian network follows the graph structure given by g. Okay, and remember, we are in the context of Bayesian networks, so we are always going to assume that g is nothing but a directed acyclic graph. So there are two types of penalties that are often used in practice. The first type of penalty is the Akaike information criteria, where phi of m is constant. Okay, what I mean by that is the Akaike information criteria does not depend on the number of data points. Okay, there is a second type of penalty which is actually used more often than the Akaike information criteria. So the Akaike information criteria is called AIC. And the second type of penalty is called the Bayesian information criteria, or BIC, right? And it's also often known as the minimum description length criteria. And here, phi of m, we select it as log 2 of m, which is log of the number of data points divided by 2. Okay, so there is a theoretical basis for choosing phi of m equals to log 2m divided by 2. I'm not going to go over that theory in this class or in this lecture. What I suggest you to do is read the book by Kohler, where these issues are discussed, by Kohler and Friedman, I should say. Okay, so that's the idea, right? So you have your log likelihood term and you add to it some penalty term. The penalty term is nothing but a negative term. So let's see what kind of models will we select when we use likelihood scores versus the so-called MDL scores or big scores. Okay, so I'm giving you two Bayesian networks. Let's call this Bayesian network T, and let's call this T1, I should say, and let's call this Bayesian network as T2. So it turns out that for a given data set, the likelihood of T1 is minus 12.1, and the likelihood of T2 is minus 10.1. So if you're using the log likelihood as your criteria, which model will you select? Remember, these numbers are negative, right? So based on the log likelihood criteria, I would select T2. Now let's look at the MDL or big penalty based on these models. If you recall, right, the big penalty is nothing but phi of m is equal to log 2m divided by 2, right? And then we have to multiply with it the number of parameters or the number of edges. So how many parameters does the first Bayesian network have? Assuming that it has that each variable can only take two values, let's count, right? So the first variable has just one parameter, right? Because the other parameter is nothing but 1 minus of that parameter. C has one parent, so the number of parameters for C is 2. D has one parent, so the number of parameters for D is 2. A has one parent, so the number of parameters for A is 2. So it's 2 plus 2 plus 2 plus 1, which is equal to 7. Okay, let's count the number of parameters that the second Bayesian network, which is T2, has. So this one has 1, C has 2 again, D has 2, but now A has 4. Okay, so the number of parameters here is 4 plus 2 plus 2 plus 1, which is equal to 9. Okay, so the MDL penalty is negative of log 2m divided by 2 multiplied by the number of parameters. So let's say we had 5 data points. So the MDL penalty turns for the Bayesian network T1 turns out to be minus 8.1, and the MDL penalty for Bayesian network T2 turns out to be log to the base 2 of 5 divided by 2 multiplied by 9, which is nothing but minus 10.4. Okay, so based on the LL score plus penalty criteria, what will you choose? Okay, we'll have to do some calculations. So let's calculate LL plus penalty for T1, right? So it's minus 12.1 minus 8.1, which is equal to minus 20.2. and for T2 it will be minus 10.1 minus 10.4, which will be equal to minus 20.5. So which one is larger? Minus 20.2 is larger. Okay, so based on the likelihood plus big penalty, I would have selected T2. Sorry, I should say T1. Right? So T1 based on MDL score and T2 based on the likelihood score. So this is the impact, right? So we are preferring actually the sparser model as compared to the denser model when we are using the MDL score. But as I said before, likelihood will always prefer the denser model. Okay, so now the question is, okay, we have a nice scoring function. If I give you two Bayesian networks and if I want to compare the two Bayesian networks, I have a nice score, right? The one that has the highest score will win. How do I use this score to generate the structure of a Bayesian network? Okay, and as I said before, since we don't have a so-called optimality guarantee, or we don't have formal results which can give us optimality guarantees such as the Chow-Liu algorithm, our search procedure will be very expensive. Okay, and if you want to solve the problem optimally, it will be impractical in practice. So what we're going to do in practice is to use greedy algorithms or local search type algorithms. Okay, but one criteria that we have to ensure that our scoring function satisfies is given on the slide. Okay, even if we use local search or greedy algorithms, we want these algorithms to be fast. Okay, and for these algorithms to be fast, what we want is our score to be decomposable over the network families. Okay, what do I mean by network family? A family is nothing but variables, or I should say each variable plus its parents. So I want the score to be decomposable over the network family. What I mean by that is that I should be able to compute the score on each family independently. Okay, so one way of looking at this is the following, right? So let's say I give you Bayesian network B1 and let's say Bayesian network B2, and let's say B1 and B2 differ in only one family. Okay, so they differ in only one family. How can I compute the score of B2 if I know the score of B1? Easy, right? All I have to do is subtract the score of family F1 for B1, right? And add to it the same family that was changed in B2. Okay? So this is how I can easily compute the score of B2 if I know the score of B1. Right? So this is like you have a large sum, right? And only one term in that sum is changing. Okay? So instead of recalculating the whole sum, what I'm going to do is just take that term out, subtract from the original sum, and add to it the new change term, and I'm done. Okay? So that's why we need our scores to be decomposable. So once we have these decomposable scores, we can either use. So once we have the decomposable score, right, we can either use the local search algorithm or the greedy algorithm, right, to solve our structured learning task. So the local search algorithm works as follows. What you do is you start with a random structure and you define the neighborhood of the structure as other structures that can be computed from the current structure by performing three possible operations. The first operation is adding an edge to the current structure. The second operation is removing an edge from the current structure. And the third operation is reversing the directionality of the arc. from the current structure. Okay? So as I said before, if the score is decomposable, then removing and adding can be done by just changing, right, one term each from the sum, while reversing, or the score after we have reversed an edge, can be computed by changing just two subscores, right, or in the scoring function. Okay, so that's how your local search algorithm will work. You start with, let's say, a random tree structure, and you keep on making these jumps to the neighbors such that the neighbor has the highest MDL score, and you stop when a local maxima is reached. The second type of search that we can perform is a greedy search algorithm, right? And this algorithm is the same algorithm that we use when we generated IMAPs, right? So if you remember, when we generated IMAPs, the way we did it is we started with a random ordering, a random total ordering over the variables, and then for each variable we selected, right, a parent set from all the variables that are ordered before that variable. Okay, so in the structured learning algorithm, we are going to select the parent set for each variable such that it maximizes the corresponding local score of xi comma ui given d. Okay, a problem with this approach is that we have to fix the ordering, right? So our the model that we learn is going to depend on how good the ordering we have used is, right? So if the ordering is bad for constructing IMAPs, for instance, right, then the ordering will also be bad for our structured learning algorithm. Now let us look at a specific greedy algorithm called the K3 algorithm. And the idea in this algorithm is as follows, right? You start with a total ordering of the variables, and then you start with an empty graph, right? So for each variable, we start with an empty set of parents. And then you run the following greedy step. The greedy step being, you successively add variables as parents until the score does not increase. Okay? At each step, what you do is you add the variable that increases the score the most. So let us look at an example. Let's say we want to figure out what the parents of x5 should be. So in the first step, what I'll do is x5, since there are only 5 variables, can have, and x5 is the last variable in the ordering, so x5 can have 4 possible parents. Okay, so I will evaluate adding each one of these edges in isolation and check what the new MDL score will be. Okay, so if the MDL score, if it turns out that the MDL score of the edge from x3 to x5 is the highest between the 4 possible parents, then I will add the edge between x3 and x5. Okay, so now x3 is the parent of x5, and this is my new network. I took one greedy step. Next, what I'll do is I will evaluate if adding x1 as a parent as well as x2 as a parent and x4 as a parent to this graph increases the MDL score of the graph. Okay, so let's say it turns out that x2 increases the score the most, right? So if you have x2 as a parent of x5, then the score is increased by the maximum amount. Then I'll add x2 as a parent of x5, right? So now x5 has two parents, x2 and x3. So my data is such that, let's say, no extension of x3 comma x2 improves the score. Okay, so if I add, let's say, x1 as another parent, right? So x2 and x3 are already parents of x5. if I add, let's say, x1 as a parent of x5 as well, the score does not improve. Similarly, if I try to add x4 as a parent of x5, the score does not improve. Then what do? Since this is a greedy algorithm, I'll stop. So now x2 and x3 are the only parents of x5. And I'll repeat these steps for all the other variables. And finally, at the end of it, I'll have a structure. And once the structure is learned, I'll learn the parameters of the model using the FOD. If the data is fully observed, I'll use the FOD criteria, right? The closed form solution. Okay, so I've not covered some advanced algorithms such as branch and bound search as well as a structural EM algorithm for learning the structure of Bayesian networks. And if you're interested in reading more about these algorithms, then you can read chapter 17 from the book by Adnan Darwish as well as chapter 19 from the book by Kohler and Friedman. And actually, I urge you to read these two chapters. So to summarize in this lecture, what we saw are structured learning algorithms for Bayesian networks, and we saw why structured learning using the log likelihood approach, right, or the MLE approach is problematic. So in order to circumvent these problems, what we saw are three types of methods, right? The first method was learning bounded tree with Bayesian networks. And specifically, we saw how the Chow-Liu algorithm can yield an efficient solution for efficient optimal solution for performing MLE learning when the underlying model is a tree Bayesian network. Okay. We also saw how to improve or increase the bias of bounded tree with networks by using latent variables, and specifically, we saw the mixtures of tree models. Finally, we saw score-based methods for learning the structure, and we saw how score-based methods or learning optimal structures using score-based methods is not possible, and therefore we saw approximate approaches such as greedy search and local search algorithm. Next class, we will look at structure and parameter learning algorithms for Markov networks.